Thank you. I got distracted sending Paige the activity. All right, so what you'll see on the slide is must knows. Not sort of kind of know, kind of have. Sit. Oh, you need an outline. Thought we were sick in the quarantine. Okay, so this is must know. Okay, there's stuff that's not on here that should know. If I covered it in class on the full slides, you should know it. But this is must know stuff. If you study nothing else, you might do okay. But if you study everything I'm going to discuss, you do better. Okay, so that's the important part. Okay, so in chapter 1, we have some basics about this. And so on that review of each chapter, that thing that's just the Word document or just words, these are the words that are on there. And so I'm going to describe each one of these as to what I mean by how these need to be. Okay, so in the case of structure and bonding, I hope you know what an atom is and what an electron is. I'm assuming you know that. Okay, so what I'm going to start with is valence electrons, because valence electrons are the most important. They're the ones who do bonding. And we need to know, we need to try to have our Lewis-Dot structures have 8, except for the exceptions. Okay, and our exceptions are hydrogen, lithium, beryllium, boron, sulfur, and phosphorus. Okay, and those are the number of electrons they might have. Obviously, hydrogen and lithium only have 2 because they only have a 1s shell. Okay, so, and we want to look for electron configurations to noble gases, right? So you want to be helium or neon or argon. So 2 electrons in the outer shell, 8 electrons in the outer shell, 8 electrons in the outer shell. That's what we're looking for. Lewis-Dot structures, there are technically 7 rules. Now, the first 4 get you through most of them. So these, go through these again, make sure that you can do your Lewis-Dot structure. The last 5 are talking about, ooh, do I need a double bond somewhere? That happens a lot with sulfur and phosphorus, occasionally with carbon if you don't have enough atoms to bond to, right? And then before you look, do those Lewis-Dot structures, you kind of want to look for other atoms. Again, put the thing that needs the most bonds in the middle and build out from there. Most bonds, next most bonds, hydrogens along the outside, okay? So, and sometimes you'll have a highly reactive molecular ion. Carbocation only has 6 electrons around it. Carbanion actually has 8 electrons around it. A radical has 7 electrons around it. So that's what that means. So that's what the 7th rule is. But most of the time, we're talking about that first 4 rules. Count the number of valence electrons, put the things that need most bonding in the middle, and then the next most bonding, and the next most bonding. So it's carbon, nitrogen, oxygen. Okay, so that's the Lewis-Dot structure. Any questions about that? You should be, go back and just double check that you remember how to do your Lewis-Dot structures. Okay, and that gives us up to formal charge. Know how to calculate formal charge. Formal charge is equal to the number of valence electrons minus half the bonding electrons, because they're shared, and minus all unbonded electrons or non-bonded electrons. Okay, now that gives us some interesting concepts, because now we can have things that are positively charged, things are not charged, and things that are negatively charged. And we see those happen a lot in the case of carbon, carbocations, nitrogen, ammonium, oxygen. When we protonate oxygen or water, we get to this oxonium cation. And then halogens can actually do it. We haven't seen it yet. You'll see it next semester. Okay, so then we have our neutral ones, and notice our lone pairs are listed there. That's important because we now have Lewis bases here, right? And then we have formal charge with -1, like our carbanions, our nitrogen anions. So this, we use this one a lot, the sodium, not that one, but we use like sodium amide, which is also an anion. And then the oxygen or the alkoxide negative ion, and the halogens, which make nice anions. Until I leave. Okay. All right. So know how to calculate formal charge. There's going to be at least. Anyway, so, all right. Know your skeletal and bond line form. So the skeletal equals bond line, but know how to convert from your condensed version to this. Like I say, when in doubt, draw it out, okay? You draw it out, it's going to be a lot easier to figure out what's happening, what's primary, secondary, and tertiary, what's going to get attacked, where your beta protons are. All these things happen when you draw it out. So make sure you can convert things to their skeletal form. And then resonance structures. We haven't done resonance structures in a while, but we learned that resonance structures give acetic acid its acidity because it spreads out charge. We also learned that in the case of the allele radicals, conjugation made it more stable, made it more reactive, made it more, and so we were able to use that in chapter 10. And then we're actually going to use this again when we talked about our Zaitsev's caveat, where you want to put things in conjugation because of resonance. Resonance gives us that extra stability, and that gives us our work. But remember, only electrons move. Okay, that means no sigma bonds are broken. You can move pi bonds and lone pairs, and that's it. Okay, you can move pi bonds and single electrons now. You couldn't move single electrons until we did chapter 10. But now you can move single electrons, so you can have an anion or a cation or a radical here. And as long as you're only moving electrons from a pi bond or from a lone pair or a single or a radical, you can get to these resonance structures. So we've actually added something to resonance in chapter 10. All right, hybridization. Know the difference between sp3, sp2, and sp1. It's easy to tell because they have different shapes. They have different reactivities. Only sp3s can go SN1, SN2. That's pretty cool. These undergo a whole bunch of different addition reactions, and we have to take something that's sp3 and convert it to sp2 with an elimination reaction. So we have substitution reactions, we have an elimination reaction to get here, we have an addition reaction to get back here, we have double elimination to get here. So we have to make sure we know all of our hybridizations. That's why I've been harping on that. It goes from sp to sp2 to sp3 because it changes shape, it changes reactivity. Okay, so the other thing about this is the character. The anion of the acetylide ion is more stable because it has more S character. Those electrons are going closer to that means that its acidity is higher than that of an alkene, and the alkene's acidity is higher than that of that. All about this S character. 50-50 in the SP, 33% in the SP2, and 25% in the SP3. Remember, we're just, adding a p orbital. So we start with one p orbital and two unhybridized p orbitals. Then we go to two p orbitals that are hybridized and one unhybridized. And then we have no unhybridized p orbitals, and we have a total of 4 equal orbitals. All right, questions on that? So that takes us to shape. Okay, so notice that the electron configuration, this is an sp3 hybridized atom. Okay, this can be carbon, nitrogen, oxygen. Okay, carbon would give us the nice tetrahedron because we got more by 4 times. Nitrogen gives us trigonopyramidal because it bonds 3 times and has a lone pair. And water gives us bend. Okay, so know that. Now notice that this is the sp2 hybridized, which will have that and an unhybridized there, or we can have boron with a bond missing and with lone pair. And then of course the linear helps us make sp hybridized, which allows us to make two double bonds because of 2 unhybridized p's. All right, so now let's compare and contrast between the pi bonds and the sigma bonds. Sigma bonds are stronger than pi bonds. A sigma bond has 2 electrons in it. I've asked that twice on exams, and it's not 100%. Nobody's getting that 100% yet. So there are 2 electrons in a sigma bond. And sigma bonds can either be sp. The sigma bonds are the hybrid orbitals, always. Sigma bonds are hybrid orbitals, always. Pi bonds are always unhybridized p's. Pi bonds are always unhybridized p's. So that means we have to have our sp3 can never have a double bond on it because it doesn't have an unhybridized p. This can only have one double bond because it has one unhybridized p. And this can have two double bonds because of its two unhybridized p's. Okay, so that is chapter 1. All your must knows in chapter 1. How many electrons are in a single pi bond? Two. One from each p. How many electrons are in a sigma bond? Two. How many are in a single pi bond? Two. How many are in two pi bonds? Four. So how many electrons are between this carbon and that carbon? 6. Okay, so you have to count your electrons, okay? Make sure. That may seem like a simple question, but write that down because it's important. All right, any other questions about chapter 1? Okay, I'm gonna do chapter 2, then we're gonna do one activity. I'll do 2 more chapters, and then we'll do our retrosynthesis activity. Okay, so we're done with that. So let's go to chapter 2. Huh? Yes, right after class, actually. Okay, oh no, that's chapter 2. There it is. All right, yeah, okay. So chapter 2 is a little bit shorter because all we talked about in chapter 2 is functional groups, families of the compounds, but we also talked about types of bonding, right? We talked about hydrogen bonding, dipole-dipole, and their effect on boiling point and melting point. Now, if you look in chapter 10, they do it again with looking at ethers and alcohols, how they have different boiling points because one can dipole-dipole bond and one can hydrogen bond. And I'll get to that when we do chapter 11. I'm sorry, it's in chapter 11. Chapter 11 tomorrow. I'll show a slide on that and review you on that. So the first things, these are all the things that are on our list there. So I've picked out some figures from other books just to give you some variety here. This is in our book right here, but know the different classifications and know what their regular functional group is and know that they can be hooked to any R group, right? Okay, so, and then you want to look at it and say, oh, hydrogen bonding, dipole, hydrogen bonding and dipole, hydrogen bond, and actually this doesn't hydrogen bond. Believe it or not, these are so close in nuclear in electronegativity that the hydrogen doesn't hydrogen bond, but the sulfur can. If something else that has a proton, no hydrogen bond, only dipole. So look at those structures and review the dipole interactions versus the hydrogen bonding interactions. Okay, so then we had our class here. Our big class is hydrocarbon. Okay, that's just hydrogen and carbon, alkanes, alkenes, and alkynes. We've done a lot of work with those already, and we've gone kind of going back and forth in between them. Okay, but then we also had these benzene rings. We talked about them a little bit. You don't actually do the reactivity of them until later. But we have benzylic positions. Benzylic radicals are very reactive. Benzylic cations are very reactive, very easy to form. So we need to think about our benzylic group, which is this plus a CH2 here. And then we can also have them in our nomenclature as a substituent. So a phenyl group is our substituent. Okay. And then we go on to halides. And primary, secondary, and tertiary halides are based on the type of carbon you have. So you got to remember, that the degrees of carbon are primary, secondary, tertiary, and quaternary. Okay, wait on. There's one more degree of carbon, isn't there? Methyl. Methyl. It's not bonded to any other carbons, but it is a substituent. So we have methyl, primary, secondary, tertiary, and quaternary. So when you're talking about alkyl halides, it's primary through tertiary because you can't, oh, well, no, you can have a methyl count, you can have a methyl one too. So it's methyl through tertiary. So there's 4 different ways to do that. So again, primary alkyl halide, secondary alkyl halide, tertiary alkyl halide, or methyl halide. You will never see a quaternary halide. You will only see quaternary carbons.
Okay.
Think about it. If you had a reaction and if, let's see, you had a carbocation on there and you put another alkyl group on there, you'd have a quaternary carbon. We haven't done that yet. You're actually going to do that next semester.
Okay, so you don't have to worry about that.
You just need to know what it is. You don't need to know how to make one yet. You will need to know how to make one next semester.
Okay.
All right. So alcohols are also based on that same premise. The OH is on a methyl group, a primary, a secondary, or a tertiary. There are no quaternary alcohols because you'd have 5 bonds to carbon. So make sure that you've done that. But here's where it gets backwards. Nitrogen causes you trouble, always. You know, nitrogen causes trouble because when you're trying to do, you know, your mass spec, it has an odd mass. When you're trying to do, when you're trying to figure out its shape, it has a lone pair, you know, so it's got some trouble. So amines and amides are backwards. It's how many carbons are bonded to the nitrogen. So in the case of amines, if there are no carbons bonded to this, this is technically an inorganic compound. Does not contain carbon. So that's why you used a lot in freshman chem. Ammonium ions and stuff like that. Okay, so the primary is 1 carbon, secondary is 2 carbons, tertiary is 2 carbons. By the way, all these tables are also on Canvas under the nomenclature review. Nomenclature review. So, okay. So then the amides, the first one is bonded to a CO. Double bond, it's bonded to a carbonyl compound is our primary. Then a carbonyl plus another carbon, not another carbonyl, that's a different functional group. And a tertiary, which is a nitrogen bonded to a carbonyl and 2 other carbons. So it's all about what's bonded to the nitrogen. Nitrogen's selfish, think of it that way. It's all about the nitrogen. Okay, so that gets us to the other carbonyl compounds. So we're going to start with the simple one, which is an aldehyde, which is 1 carbon, 1 hydrogen. The ketone, 2 carbons, then a carbon and an electronegative atom. This sets the stage for all of the carboxylic acid and carboxylic acid derivatives. Okay, so we have the ester, which is similar. We have the amide, which is nitrogen, and we have the acid chloride. What's the one functional group that's missing from here? Well, the other functional group that we have that's related to this is actually the nitride. It's if you took this and removed water, you get a nitrile. So nitrile is the other functional group. So I technically put it as a classification of a CO derivative, a carbonyl derivative. All right, which brings us to intramolecular forces. Okay, melting point, boiling point. And solubility. Like dissolves like. You want a non-polar material to dissolve non-polar materials. Because all they have is van der Waals forces, London forces, or dispersion forces. Those are all the same words for induced dipole, induced dipole. Our book uses induced dipole a lot, but it's also called a dispersion. Then the next strongest one is dipole-dipole, because you have a permanent dipole. And so the positive, partially positive side lines up with the partially negative side and raises the boiling point. Then next we have hydrogen bond, which can bond a lot of times and therefore really increases the boiling point, assuming all the masses are the same. So if masses are different and they have the same type of interaction, the higher molecular weight is going to be the higher. And then there's a caveat to that in alcohols, and we'll talk about that on tomorrow. Then there's ion dipole. We use this a lot. Remember, the ion dipole interaction is why we want to use polar protic solvents in SN1 reactions. It can solvate the cation and the anion. You want to solvate both. So that's a very important interaction for us. Covalent bonds are stronger than that. Carbon-carbon bonds, well, maybe not oxygen-oxygen bonds. They break apart all the time. Right? And then we have our cation, anion, and they're so strong, it's almost impossible to melt them sometimes. All right, questions on interactions. The last thing we learned in chapter 2 was IR. And know your zones. Know what bonds are in which zone. Okay. The 4,000 to 2,500, only heavy atom hydrogen bonds. Carbon hydrogen bonds, carbon-carbon double bonded to a hydrogen, carbon-carbon triple bonded double to a hydrogen. Note that they have different places in that spectrum. Oxygen, hydrogen bonds, and nitrogen has one peak if it has one hydrogen on it, two peaks if it has two hydrogens on it, zero peaks if it has zero hydrogens on it. Then, of course, our triple bonds are next in the 2000 to 2500, the double bonds 15 to 2000, and then our single bonds down here in the fingerprint region. You want to try to identify your type of bond you have in the first three zones. And that, again, it's not functional group, it's the type of bond. So if you had a carboxylic acid, you have to have something here and something here. Okay. If you had an ine-ol, an alkyne and an alcohol, you have to have something here and something here. Okay. So remember that it's not about functional group, it's about type of bond. Okay. All right, questions on IR? All right, so that's chapter 2. So let's do our first activity here. And this is a synthesis activity. I start with the same substrate, and I want you to identify the reagent that correctly converts that reagent into that product. Now, the reason I do it this way is I don't want you to worry about, oh, we've got a different R group on it. No, it doesn't matter. You're looking for the change. Look for the change. If you're worried about the R group, don't worry. You just rewrite the same R group over. You want to look at that change. And that way, you will be able to realize how to do this. Okay. So there are a total of 8 reactions on here. We know every single one of these reactions now, by the way. And they should all be on your reaction table. And they are all on my massive PowerPoint of doom, which has every reaction up through chapter 11. I'm up to chapter 8 so far. So I'm working on it. Okay, so let me go ahead and I'll pull up one of these things and share that file here up on the screen so we can pay attention. Let's see, Microsoft Word. That's the retrosynthesis activity, synthesis activity. And I'm going to share that screen. Oops, wrong one. Stop share. And okay, let's get it a little smaller so the whole thing fits on the screen. And I will post the key to this and the retrosynthesis after this class. I just haven't actually done this one yet, so I thought I would do it when you guys are working on it. We'll give you about 10. We're going to go till 10:35. Okay, unless you're all done. Tell me if you're done. Remember, some of them require a certain solvent, like a polar acrylic or a non-polar or non-halogenatable. So I have the key now. Maybe I need a hint. So notice this is know your reactions from the middle. Stop share. I'm gonna go load this onto Canvas right now. So that okay, it'll be under activities if you want to do it again. Mhm. All right, got about 1 minute. So if you have any questions, go ahead and ask them now because I can help you while I'm here. But I will be posting the key. Actually, I can post it now, I guess. No, I'll post it after class. And so it'll be a copy of both retrosyntheses and both retrosynthetic keys will be on there. And then this is the synthesis activity that'll be also on there. It's going to be under activities under games. All right. So what you should do is then go study and try to do this again. And I thought you do it fast. And if you can do them where you can answer them all very quickly, then that's going to be good. Okay, let's move on to chapter 3, acids and bases. Chapter 3 review. There we go. I'm going to go ahead and share my screen. Screen sharing is paused. And there we go. Chapter 3. So the things we're covering in chapter 3 are the different types of reactions, Lewis acid and Lewis bases, which are also nucleophiles and electrophiles. But then we also have to know Bronsted-Lowry acids and bases, because that's how we tell whether the reaction's going to go, right? We're always going to go to the weakest acid. So we're going to transfer, we're going to measure the conjugate acid and we're going to look up on a table, the conjugate acid with the starting acid, see which one is the weaker acid, and you'll know which direction the reaction's going to go. Nucleophiles and electrophiles, trends in acidity, the element, hybridization, inductive, and resonance effects for acidity, and then equilibrium constant and free energy trends. Okay, so you'll need to know these definitions. Substitution, addition, elimination, and rearrangement. We've done all of these now, right? We've done all of these now. But also know what a reagent is, a substrate is, starting material, product, reaction mechanism, concerted reactions, and stepwise reactions. We've used all of these too. So these should be familiar, but just double check, make sure you know what concerted means, or substrate and reagent. Okay, so there are only 5 patterns in a mechanism when we're talking about moving 2 electrons. There's only 2 patterns in a mechanism when we're talking about moving 1 electron. So that's good, right? So we want to make sure we know all of these. We also want to make sure we know our arrows. The reaction arrow is a single arrow. This is an equilibrium arrow. This is a resonance arrow. This is moving 2 electrons, and this is moving 1 electron. Okay. Again, we've used all of these arrows. The other arrow that's not on here is the retrosynthetic arrow, which is the 2 lines with the bird's mouth in it. And we'll use that in a few minutes. Okay, so Lewis acid, an electron pair acceptor to form a new sigma bond. A Lewis base, an electron, wait, that's bad. Yeah, no, that's right. A Lewis base is an electron pair donator to make a new sigma bond. So that means that all Lewis acids are electrophiles and all Lewis bases are nucleophiles. And so we can just have a bunch of reactions. Notice this compound here, you know, even though it has 2 charges, it's a neutral compound and it has a sigma bond. Okay. So the other thing we need to know is our Bronsted-Lowry acids and bases. So if you start the reaction with an acid and a base, you're going to get a conjugate acid and conjugate base. And by looking up the acidity of the acid and the conjugate acid, you can tell which direction the equilibrium lies. The weaker the acid, the more it's going to lie to that product, okay? Now, what we're looking for here is in Bronsted-Lowry, we always transfer a proton. That's why we have a different definition for Lewis acid and base, because you do not transfer a proton. In fact, you can actually do the Lewis acid base reaction and have something that has to lose a proton to get back to neutral. For example, when we do reactions where we're having water attack as a nucleophile, we get the oxonium cation, and it has to lose a proton. So we had a Lewis acid-base reaction first, and then a Bronsted-Lowry acid-base reaction second. Okay, so make sure you know the difference between the two. One transfers a proton, one just makes bonds. Okay, so know the four factors. Element. The more electronegative it is, the more acidic it's going to be, right? So we're moving up to fluorine, but wait, hold it. That's not the only thing. So it's also size. So we're looking at, as we're going across a row, acidity increases. We're going from boron to fluorine, acidity increases. But when we're going down a row, acidity increases. Okay, nucleophilicity just goes up and over. Acidity goes over and down. Make sure you know the difference between the nucleophilicity trend and the electronegativity trend is slightly different than the size trend, the acidity trend. Next is hybridization. That's specifically for sp3 is less acidic than sp2, which is less acidic than sp1. And it's all because of S character, okay? Resonance, the more you can spread that charge out. Think about that methane sulfonic acid. What made it a great leaving group was the fact that it could spread that charge out over 3 different oxygen atoms, making it a very acidic compound, which makes it a very weak base, which makes it a great leaving group. And then inductive effects, that's pulling through sigma bonds using electron donation or electronic drawing. We demonstrated with electronic drawing, making them more acidic. Adding electrons to the system actually makes them less acidic. They're less stable. All right, questions on factors? Okay, now, do not memorize this chart, but know the trends. Know that as you get know as your acidity increases, your basicity decreases, okay? But you should know these by class. Carboxylic acids, pKa 5. Phenols, pKa 10. Why? Resonance. Resonance. Alcohols and water, pKa 15. Why? Because the charge is stuck on the oxygen here, it's resonance here, and it's spread over 2 oxygens here. So that's why our trend is here. And now these are alkynes, alkenes, and alkanes, 25, 45, and 60, respectively. And that's because of 50% S carrier, 33% S character, 25% S character. Okay, that's the great way to remember these, okay? And luckily, they go by 5s, 5, 10, 15, 25, 45, and 60. So you don't have to remember 17.3. But also put alcohol out is also right there with water. You can put water here as well. Okay, so those are the ones you must know. All right, so then we did kinetics versus thermodynamics. And in a thermodynamic system, you can have equilibrium, okay? And we have to measure our equilibrium constant based on the products divided by the starting materials. That means the concentration, that equilibrium constant, no matter how much you started with any of them, it's going to get to some point where it's going to have the same forward reaction as backwards reaction. And that gives us our equilibrium constant. But then we also have to think about that equilibrium constant is also controlled by this. We said that the Gibbs free energy change is approximately the same as the enthalpy change, basically the heat stored in the bonds, okay? Except in the case of high temperature reactions or a big change in disorder. Imagine we had one of those polymers we built with radical polymerization. So we have one molecule that has 1,000 of them, right? And then we break out every single one of those monomers. So now we go from one thing to 1,000 things. The change in entropy is huge. So it pays a factor. And we did the reaction to break it up like that at 500 C, which is 773 Kelvin. So it is really, that's when we have to pay attention to that enthalpy term and that temperature term. All right. And that's really kind of the bulk of what you have. Now, remember, go back to your reaction, looking at in chapter 6, looking at the change in the change in Gibbs free energy or the change in enthalpy. All right, I'm going to do chapter 4, and then we're going to do our retrosynthesis. In chapter 4, we're talking about nomenclature. We learned how to name many different classes all the way up to alcohols and some alkyl halides and stuff like that, right? We also learned alkenes with alcohols on them, enols, and alkynes with alcohols on them, inols, okay? So we'll look at all of those, plus our cyclos and our cis-trans isomerization, and then our Newman projections, chair and boat, reactions of alkanes. We actually have a couple reactions, 3 technically reactions of alkanes, and then degrees of unsaturation. So let's talk about the rules. There's an entire thing on Canvas called All the Rules of Nomenclature. Okay, now the rules are a little bit different because we actually started with find the longest chain. I've added this one to look for the functional group, because if it's an alcohol, it changes the name, so we need to know that. And then we have to know priority. And at the end of that review, there you'll have all the priority of those functional groups. We only have to go up to alcohols, which is not bad because alkyl halides are always substituents, right? Ethers are always substituents. And then the next thing is alkanes, amines, then alkenes, alkynes, and alcohols. Alcohols are our highest priority thing right now. Okay, so then go through all the rules. Don't forget your di, tri, tetra, but you also need to know your alkyl groups. You have 1, 2, and 3, 4, and 4 for this, but you have 2 isomers of 3, 4 isomers of 4, and then you have a whole bunch for 5. But we're not going to worry about that. The only one you have to worry about that is on the slides, which is neopentyl. Okay, so note that these are substituents. These are parent chains, right? It has A-N-E at the end. Substituents have the Y-L at the end. So make sure you remember that. Oops, okay. And then cycloalkanes. Remember that cycloalkanes have ring strain. Most ring strain, a little bit less, no ring strain. And why? Because when we drew our Newman projection, we found out all of the bonds were either gauche or at least not eclipsed. And that's why it's so good. But also remember there's a cis and trans isomerization in rings. Because we don't have free rotation, they're either both going to be on the same side of the ring, cis, or on opposite sides of the ring, trans. Okay. But then remember about numbering. When you only have 1 substituent, it's always at the number 1 place. When you have 2 substituents, you need to have it at the lowest number possible. And write this down. If you have an alkene, you have to number the first 2 in the ring, the carbon 1 of the alkene and carbon 2 of the alkene. Okay, so you have to number 1 and 2 of the double bond in a cycloalkene. Okay, double check that rule. We did it in class. Okay. Okay, so then we had bicyclos, and bicyclos are kind of fun. We learned how to draw them by drawing the bridge heads first, then going around and drawing all 3 of your bridges. And you know how to do that because your bridges are in the bracket here. You're going to have 3 carbons in one bridge, 2 carbons in the second bridge, and 1 carbon in the third bridge, in this case here. If it was 1, 1, 0, then you have to go 1 carbon on this bridge, 1 carbon on that bridge, and now bridge heads are attached together. So remember your numbers for your bicyclo compounds. Also remember your numbering order. You start at a bridgehead and you move all the way around the largest ring first, the second largest ring second, and the third largest ring third. So even though you want to say, I want this to be number 1, it's not, because that has to be number 1. And then you have to go around this ring first, that ring second, and then this ring third. You could have started here and just gone around the other way, but this is always going to be 8. Doesn't matter. But start with your bridgeheads, add your bridges, and number accordingly.
So like, as far as the ACS goes, do you know like how much of each chapter will be on there?
Well, okay. it's not really, I don't know. Let me say that first. Number two, we chose this book because it had almost all the information for this half of the course on that first exam. So I believe you should have been exposed to 95% of that. In fact, I only think there's 2 questions on there that we didn't actually get. So, and we exclude those, and that counts because that's why we curve it. But you should have been exposed to everything here. Now, I might stress things a little differently because I'm not going to teach the test, but I'm going to stress things that I think you need to know for next semester. But you should recognize everything. I actually gave somebody in the first year class a second year one, and I said, don't worry if you don't recognize things. And she was like, I don't recognize anything. Wait, oh, that's an option. And so I had to immediately, as soon as I found it, I had to call her and make sure she wasn't suicidal. You got the wrong exam. Like, good, I didn't recognize any of the questions. So, but we're not going to do that. You're going to recognize most of the questions, okay? But as far as which chapter, I would definitely, I think the synthesis side's a little harder. Nomenclature, you got to get rules down. And remember, we're going all the way up to alcohols, naming alcohols. So,
is it all multiple choice or is it choice?
it's all multiple choice. 70 multiple choice questions, 110 minutes. Okay. All right, and it's Wednesday still? Okay, good. All right. So let's talk about systematic alcohols. We have the systematic of alcohols where alcohol changes the name. So we have OL at the end. We use all the other rules. So basically, this is our new rule number 1 is we found out it was an alcohol and changed the name. So then we use all our regular rules, but then we also have diols, triols, and tetraols. And again, when we have rings, we have cis and trans diols. In fact, we learned how to make cis and trans diols in chapters 8 and 11. We learned we can make cis diols with osmium tetroxide, and we can make trans diols with epoxies and ring opening. Okay, so definitely done that. Your alkenes and alkynes, both carbons must be in the longest chain. In the rings, both carbons have to be enabled 1 and 2. Okay, and then if you have more than one in there, you have to add names. So for example, we have an alkyne and an alkene, but alkanes, alkenes, alkynes. But guess what? Alcohols are over that. So you still have to use your, like if there's an alcohol over here, we'd have to say 5-methyl 4-hexene 1-ine 1-all. So you just add them all together. Follow the rules, just keep adding them together. And then diines and dienes, if you have more than one. Again, long chain. And because we don't have rotation, we have cis and trans isomerization. Until you add more than 2 groups, then we have E and Z. So then we have E and Z. Okay, halides are easy. Primary, secondary, tertiary. You just do your parent chain first. It's a substituent. You don't control the numbering by it. You control the numbering by your rules. This is only 2 because that would make this at a low. This would make, if we started from this side, be a 3. So the chlorine is not controlling the numbering. The substituent numbers are controlling the numbering. Okay. And of course, you can have dichloro, trichloro, tetrachloro. All right, questions on nomenclature. Okay, go back and do the RNS activity and do the activity on the back, which is E and Z. Okay, and go back and do the nomenclature activity. You can do the whole thing now. We have bicyclos and we have everything now, so you can do that entire activity. The one thing you won't know is probably the oxo, which is the carbonyl compounds. Right. Okay, so then you got to know your Newman projection. Know how to draw it. The front one's the stick. The back one's the sphere or the circle. Know that you have eclipse, gouge. Let's see, the other one, staggered. We have different kinds of gouge. We can have the gouge where they're close together, and then we can have them on the other side. Know what anti is. Okay, here's anti. eclipsed, gouged, eclipsed, gouged, eclipsed, and okay. And the relative energy barriers there. Think about it. The more, if you have the two biggest groups, eclipse, that's going to be the highest energy. Two groups anti, that's going to be the lowest energy. And gauge is somewhere in between. Okay, then we talk about cyclohexanes. And cyclohexanes have no ring strain, because if we drew the Newman projection, we would see that this is going to be anti to this, and this is anti to that, and we only ever have a Gauss interaction between these things here, so it has no ring strain. But it tells us a lot about where it is. Now remember that we have two kinds of positions on a cyclohexane. The axial position is the one that's like the axis on a globe. The equatorials, or if you're spinning the hexane around your finger, the ones on the outside are equatorials. But then when you're going from chair 1, all the axials convert to equatorials in chair 2, and all the equatorials convert to axials in chair 2. So know that you flip back and forth that way. And so that way, when we do our flipping, we're not saying, oh, look, we have our equatorial here, we have an axial here. Now, we also need to think about stability here. You want your biggest group in the equatorial position, because it butts up against the hydrogens on the top. There's also a hydrogen here that we butt up against. Questions on equatorial versus axial and cyclohexanes? Okay, so we actually have reactions. We go back and revisit this reaction in chapter 10. We revisit this reaction in chapter 8. So really, we only touched on them. They are actually in the book. And so, but I said, don't worry, we're going to do this in chapter 10 and this in chapter 8. And then the other reaction we have is combustion, which is boring. We don't need more CO2. We want to do less of this here. Okay, questions on the reactions? That leads us to the last big thing, degrees of unsaturation. In a hydrocarbon, you would have CN, and then your hydrogens are going to be 2N plus 2 for a non-cyclic, non-alkene, non-alkyne. Okay? By closing a ring, you lose 2 hydrogens, so it becomes C to the N, H to the 2N. And we can use that formula to decide what our degree of unsaturation is. Okay? Degrees of unsaturation are how many rings, how many double bonds, or how many rings and double bonds do you have? How many triple bonds do you have? You can tell all that from degrees of unsaturation. So a ring is an unsaturation of 1. An alkene is an unsaturation of 1. An alkyne is an unsaturation of 2, right? So we have a formula, and this is the simplified formula here, but I wanted to draw it out again, that you have 2 times the number of carbons, which is N. N is the number of carbons, okay? Then plus 2, which is the 2 from our CnH2 plus 2, 2N plus 2. Then this is our 2N. This is what we're looking for. And then the number of hydrogens. Okay, so we have to look for this X here. So when we do this, we have to remember that oxygen, we don't care about, we just ignore. Nitrogen, because it bonds 3 times, we actually have to subtract 1 for it. Halogens are exactly the same as hydrogens, because they only bond once, okay? So we need to remember those rules. Don't care about this. Halogens count as hydrogens, and the nitrogen we have to subtract 1 because of the thing. So this is another rule for nitrogen that screws everything up, right? Primary, secondary, tertiary is backwards. We have to subtract 1 for nitrogen here, and the nitrogen rule in mass spec. So it all kind of ties together. So here we're going to convert this to a hydrogen, so it's going to be 7 and 12. Here we're going to subtract 1 to get to here because we have a nitrogen, so we're going to be 5 and 8. And then when we look at our degrees of unsaturation, we end up with 2. So our degrees of unsaturation here is we have a ring and a double bond, 2 rings, a triple bond, or 2 double bonds. That's unsaturated 2, the same thing here. Okay. So just because you get to your degrees of unsaturation You know, if there's probably going to be a question like, you know, how many degrees of saturation does this compound have? And you have to go. You count the hydrogens, you count all the oxygen. Well, you make the empirical formula and then do calculation. You do have to remember the equation though. You can immediately write it down on when you get in the exam, but on your scratch paper, do not write on the exam. All right, that is number 4. So now let's look at our retrosynthetic. I have been nice. I've showed you how many steps. And so you're going to fill out what not only what the compound is, but what the reagent is for each of these. Okay. So what you want to do is take our strategy of what do I know that makes that compound and what was the starting material. So now we're having to work it both the middle and the forward and backwards all together at the same time. That's why retrosynthesis is a challenge. It's not hard. It's a challenge. You just need to use your method. Now, there is a retrosynthetic slide on, I think it's chapter, I think I put it in chapter 11, the rules of retrosynthesis. You write down the change, look for the change in functional group. Did a ring open? Have you more carbons than you had before? You need to look for that. So like in the second one, you have more carbons than you had before. In the first one, you had a ring and you changed the ring. In the second one, you have a funky group there that you have to figure out how to put on there. And how did you convert from an alkene to 2-alk to a diene? So go ahead and work on this ask question. So go ahead and pull up the retrosynthesis. If you have questions, just chime in. And then we'll give you, let's give 20 minutes for this. Okay. This is where your reaction table, doing your reaction table helps. Because you start to recognize, oh, wait, hold it. If I had this, I could make that. And then if I had to back up one more time, how would I do it? And I will post this key tonight too. Oh, after class. Oops. A couple of my arrows are in the wrong direction. So this is the retrosynthetic arrow. So I get the context. You can use your reaction tables to do this one, but you need to revisit it and see if you can do it without your reaction tables. You'll have to fast forward through this if you review this video. I don't want to pause it because I'll forget to put it back on. question. Got 10 minutes left in class. Carrying on with our last chapter. About 2 minutes. So let's. All right. So let me give you a couple hints on this. So obviously the first one, we want to do some kind of permanganate oxidation of a ring. So we have to make an alkene. We're starting with a hydrocarbon, and we only know 2 reactions on hydrocarbons, right? One is a radical halogenation to get it, and then base to get the alkene, and then that. Second one is a deprotection. So we learned this in chapter 11. We have to protect that alcohol because we have to do reactions with alkynes in non-protic solvents. So we had to protect it with the T-butyl group and then clip it off. The last one, we're probably going to do HBr to give us a functional group there. Or bromine. No, HBr. No. We're going to do radical halogenation. Okay, but we have to use NBS because that's going to give us an allylic bromine on there. Then we'll hit it with the good nucleophile. CN, the only thing we have for that is an SN2. So you knew you had to do it in SN2. So you need an alkyl halide there. Then you're going to dibrominate the double bond, and then you're going to use 2 equivalents of base to get to a conjugated diene. Remember, we got to conjugated dienes. That Zaitsev caveat is you're going to deprotonate one of them. It's going to make a double bond. You're going to deprotonate the other one. It'll make the other double bond. So that's how the strategy works. So using those hints, go ahead and do it again. And I'll post the key later today. All right, so let's get on to chapter 5. Chapter 5 is all about stereochemistry. So it's a lot of definitions, right? So we're going to look at R and S and the priority rules. Luckily, the priority rules are the same for E and Z. And so when we go to chapter 7, we're going to talk about E and Z again. But then we have to know our different projections, our stereo. Oh, am I sharing? I'm not sharing, sorry. You're just watching me walk around the screen. Sharing. 1, 2, 3. There we go. So we're going to do our R and S, and whichever way you want to do it, pinwheel method. If you don't like my hand method, go to myorganicchemistrytutor.com. He does the pinwheel method. Just make sure that you're paying attention if it's rotated around. You have to get it in the right orientation. So, for know your stereo, your Newman, and your Fisher projections. We did Newman in the last chapter, but our stereo projection is the one you're going to see for chiral compounds. And then your Fisher projections are best if you have more than one stereo center. Okay, and your Newman projections, we use those again in the alkene chapter because we have to have our leaving our hydrogen and our leaving group have to be anti-periplanar. Okay, then know the definitions of enantiomers, diastereomers, and meso, definitions of chiral and achiral, and then the racemic mixtures and rotational light. Okay, so we only have 4 rules for prioritization. Z number. Go out until there's a difference. The highest Z number wins. If you have double bonds, they get counted twice. And then if you have a high isotope, it's a higher mass. And then 1, 2, 3, 1, 2, 3 clockwise is R. 1, 2, 3 counterclockwise is S. All right, projections. Make sure that when you draw your Fisher projection, you draw it correctly. Sometimes you'll see them this way. In fact, on the last exam, you had to redraw it correctly where the longest carbon chain is vertical and all the attachments are horizontal. And all those attached horizontals are facing out toward you. So if you have to assign R and S, you think you need to know that those 2 horizontal groups are facing at you. Okay. This, a lot of people got that wrong because they didn't rotate this up. So all you have to do is redraw it where this is up, this moves over here, and this moves over here. They all rotate in the same direction. I don't know. Email me if I did. Okay. And then, of course, our Newman projections help us tell a lot of things. We want to get anti-periplanar for our elimination reactions. We want to be anti for our lowest energies, etc. Okay. Isomers. We have different kinds of isomers. If they have the same empirical formula, they are probably isomers. And so we have either constitutional isomers bound differently or stereoisomers. Now, stereoisomers encompass 2 different things. We have R and S, and then which are optical isomers. And then we have cis and trans, or E and Z for alkenes, because those are stereo. Remember, stereo means space. So they're fixed in space with no rotation. So we're going to have those as also stereoisomers. And then if they are non-superimposing mirror images, they are enantiomers. They always come in pairs. There are no meso enantiomers. They always come in pairs. Okay, but once you have more than one stereocenter, now you have to start looking for mirror planes and whether or not you have a superimposable or you have a mirror plane, which turns it into a meso compound. And then you also need to remember that there's a difference between chiral and achiral. Chiral must have 4 different things on the carbon. If it doesn't, or this, whatever the center you're looking at is, it can be nitrogen too. If it doesn't have 4 different things on there, you don't have to do anything with R and S, it's done. You're out there. But an achiral center does not have 4 different groups. Okay, and then once you get to diastereomers, again, you have to look for those mirror planes. That happens in rings too. Certain isomers of rings have mirror planes, certain isomers of rings don't. And so we'll need to see that we have our first pair of enantiomers. And this is pretty close to a Fisher projection, right? Where we have this so that we know that this is the mirror image. And then to get to our other set of enantiomers, we just move one of the groups. One of the stereocenters we invert to get to our other stereocenter. Unfortunately, this one does have a superimposable mirror image and it has a mirror plane. So that turns this set of enantiomers into not chiral meso compound. So we only have a set of 3 isomers for this compound. We have the pair of enantiomers, and then the diastereomer has a mirror plane, so it's a meso compound. Okay, does that make sense? Diastereomers, think about di meaning 2 or more stereocenters, and so you're going to have that. And remember also that if you have 2 stereocenters, it's 2 to the n. So 2 times 1 stereocenter is 2 isomers. 2 times 2 is 4 isomers, unless you have a meso plane. And then 2 times 3 is 8 isomers. So it gets crazy after 3. So then you need to know the reason they're called optical isomers is the only way you can tell them apart is through the rotation of planarized light. Okay, and if you have a pure R, it's going to rotate light one direction, and its enantiomer, if it's pure, will rotate it equal and opposite. equal and opposite. Okay, but if you have a little bit more one than the other, we have what we call enantiomeric excess. That means that if you have 10% of the other isomer there, it's going to cancel out 10%. So 20% of the signal is now canceled. So you're only going to have 80% of your original signal. And that's what an enantiomeric excess is going to see. So you have 90% of one isomer, 10% of the other, but it's going to give you an enantiomeric excess of 80. And then, of course, this just is telling you we have to pay attention to our light, our path length, and our concentration with our observed. Most of the time, we're giving it as the specific. So this is specific rotation. This is observed rotation. All right, questions on stereochemistry? All right, well, we're now at 11:30, and so that is the end of review part one. Do you think the activities are something that are going to give you an idea of how to study for this? Okay. All right, I'm going to start incorporating activities every single week in my long class too. So, because you guys need to really do better after that. All right, see you tomorrow. I will post the video and I'll look and see if I don't have keys posted for something. I'll post them now so you have an opportunity. I did post quizzes for my chapter 10 quiz and my chapter 11 quiz, so you can look at the type of questions, and I posted the keys to make sure you're figuring out the correct answers, okay? So those should all be under resources. The activities are all under activities. The activity keys are under key activities. So those will all be there. Yeah, and that should be everything. All right. Thank you very much, and I will see you tomorrow. That's a question. Yay, all right. All right, in for all.